Problem 25 on page 242. Let's read the problem. It says, Brutus, a champion weightlifter, raises 240 kilograms of weights a distance 2.35 meters. A, how much work is done by Brutus lifting the weights? And then B, how much work is done by Brutus holding the weights above his head? C, how much work is done by Brutus lowering them back to the ground? D, does Brutus do any work if he lets go of the weights and they fall back to the ground? And E, if Brutus completes the lift in 2.5 seconds, how much power is delivered? So I think what I'm going to do is do a find and solve for each part. So for part A, it says, how much work is done by Brutus lifting the weights? So we want to find the work done lifting. So let's solve. Well, work equals force times displacement. The displacement is up, so I'll call it delta y, times the cosine of the angle between the force and the displacement. But he applies an upward force to the weights, and that is the direction of the displacement. So the work done is just the weight, which is 240 kilograms, times 9.8 newtons of force per kilogram of mass, times the cosine of 0 degrees. And so let's figure out the weight, and we're probably going to need that number. So 240 times 9.8 equals 2,352. And, oh, I forgot to multiply by delta y. Delta y is 2.35 meters. Okay, so that should have gone there, but the order doesn't matter. And so times 2.35 meters equals, and then, of course, this is 1. Cosine of 0 degrees is 1. And so you get the work done as being 5.52 times 10 to the 3 joules. And let me check my answer there. Yep. Now for part B, what are we trying to find? It says, how much work is done by Brutus holding the weights above his head? Work holding above his head. And solve. Well, again, work is equal to force times displacement times the cosine of the angle between them. But what do we know? If he's just holding it above his head, what's the displacement? I mean, we know what force it is. It's 2,352 newtons he has to apply to those weights. But he's just holding it there. So he's not doing any work on the weights. The delta y is 0 while he's holding. He's not changing the position at all. So the answer is 0, or work equals 0. And then for part C. So now, by the way, he is expending energy, right? I mean, if you hold something really, really heavy over your head, you're going to get really tired, and that's because your muscles are twitching and, contracting, and the energy in your muscles, though, instead of doing work on the weights, it's heating up. You're just creating a lot of heat. You're heating the environment, so your energy is going into the environment, but you're not doing any work on the weights themselves. You're not transferring any energy, any additional energy into the weights. So for part C, how much work is done by Brutus lowering them to the ground? So find work lowering weights to ground. Okay. Well, let's solve that. Well, again, work equals force times displacement times the cosine of the angle. Now, the force is 2,352 newtons. And you're lowering it down by 2.35 meters. Now you might be tempted, because you're lowering it, to put negative there. Don't put negative there, okay? When you're calculating work, it's the magnitude of the force times the magnitude of the displacement. And but then we go cosine. What is the angle, though, between the force and the displacement? Well, as he lowers this weight, he's still pushing up on the weights with 252 newtons, or I'm sorry, 2,352 newtons. But the displacement is now down. So the force is up. You know, here are the weights. Okay. He's lowering it at a constant velocity, but he's lowering it down. So here's the force, but here's the direction of the displacement, delta y. They're at 180 degrees from each other. The force and the displacement are in opposite directions. And a cosine of 180 degrees is -1. So it's just this times -1. That's going to be negative 5.52 times 10 to the 3 joules. He did negative work. Now what he did is he took energy away from the weights. What kind of energy? Well, it's gravitational potential energy, which we're going to get to in the next unit. We're going to discuss that in the next unit. Okay, part D. Does Brutus do any work if he lets go and it falls back to the ground? So find work done if Brutus lets go. Well, again, you know, work is force times displacement times the cosine of the angle between the two vectors. Oops, if I'm off screen, let me know. But if he lets go of it, is he applying any more force to the weights? No. So this is 0, even though this is, you know, 2.35 down and so on. So he's not doing any work. What is doing work on the weights when it falls back down? Gravity. Gravity is doing work. So, of course, gravity is doing positive work on it, but Brutus is not doing any work for part D. And then part E, we want to find the power if Brutus lifts this weight up from the ground up to this 2.35 meter height. If the time it took to do that was 2.5 seconds. So let's solve. Well, power is the work done by Brutus divided by the time it took. So the work done by Brutus, we figured in part A, and the time is 2.5 seconds. So the power will be 5.52 times 10 to the 3 divided by 2.5. If you round it off, it's 2.2 times 10 to the 3 watts, or 2.2 kilowatts. 2.2 thousand watts. That's a lot. That's a lot of watts. What we're going to do a lab later on where we're going to run up the stairs and you're going to figure out how much power you put out while running up the stairs. I think the biggest power I ever got from a student was about 1.7 kilowatts or 1,700 watts running upstairs. So if Brutus can do that, and I think this is pretty realistic, that's a lot of power. Very, very, very powerful. But look at him, you know. course, I don't know. I think all those steroids are probably going to do damage to his long-term health. But for now, anyway, he's a powerful, powerful man. Any questions? Okay, that is all.